Welcome students. In this video we will talk about combinatorial functions and different ways of implementing them. So what is a combinatorial logic? Basically it's when you have a specific combination of inputs, you only have one possible output. You have seen this when we have had logic truth tables. For one row there's only one possible output for the system. So when we're going to design a combinatorial circuit, what we have is something that is different from what we ideally think. So for example, let's think of a NOT function. A NOT function, this is a graphic that has the voltage through time. So if you have a signal that it's 0 here, and then at some point it goes to high, or a logic 1, then a NOT function, ideally, it's when the input is 0, the output is going to be 1. And when the input is 1, well, the output is going to be reversed or inverted. However, a real implementation, it's this. When you have a sudden change in the input, what you're actually going to have is a continuous response. In this case, this continuous response has a time in which it's going to change from low to high or to high to low. This is usually from 30 to 15 nanoseconds. It's actually very, very fast, but you have to consider this, especially when you're designing these types of circuits. So when we have electrical signal and logic values, you know already that we typically use terms in respect of voltage, being H and L, which stand for high and low. We usually design or use these terms to represent the logical values 0 and 1. There are two conventions, as I have already explained to you, which are the positive logic, which uses the high voltage to represent an on signal, and we have the negative logic, which uses the low voltage, or 0, to represent the on state, or the active state. As a symbolism, we use the negative logic signal with an inverted variable. For example, there's a very common signal that is called a reset, and usually reset is put with an inversion on top of it. So this means that there is actually a need of a 0 volts in order for this signal to be active. These are the electronic gate symbols that we will be using for logic gates. You can see that we have two conventions. These are the most common ones. However, these are also used. And this convention on the second column, it's called the IEZ. In this slide, we have already talked about AND, OR, and NOTs, which are the basic functions, but you can see that I'm also talking about NANDs, NORs, and XORs. So we also have these three types of functions. And it is important that you know them, and in this video we will cover specifically how the NAND works and how we can implement functions using only NANDs. Let's suppose you're asked, design a logic system for a machine to dispense coffee, tea, or soda. However, the machine has different push buttons. In this case, it has one push button for a coffee, one push button for the tea, and one for the soda. So you need to design a logic system that ensures that the customer can have at most one of these three choices. So picture a box. You have a physical box where you have a vending machine, and in this machine you have three buttons. So here we want to design a system that tells me, well, the person that is in front of this machine can only push one button. At some point, one customer can push two or more buttons in this machine. So you want to make sure that in our logic system, we make sure that we don't allow that. If we detect more than one choice, we're going to deny the product to the customer. And we're going to ask them maybe to push only one button. So we're going to design the circuit that ensures that this happens, that at most one condition is met. So what is a truth table? The truth table is this. We have three choices, coffee, tea, and soda, and we have the function, which in this case I'm naming the function at most 1. So basically you can see that the system or the truth table is pretty simple. When we have only one choice, we're actually going to put a 1 in the function at most 1, because we don't want, for example, if we analyze this row here, in this row here, the customer has pressed both the coffee and the tea buttons. So we're going to put a 0 here because we're going to say, okay, this is not correct. We need the customer to just choose one of the product. So in this case, the function is very simple. We have seen how to get this. I'm naming my function at most1, and this function is equal to the sum of mean terms 1, then mean term 2, and mean term 4. Using what we have learned, we will try to minimize this function by putting it in a truth table, and we have that came up. If we try to group this, the only way we can group this is, well, if we group them individually. So in this case, well, there is no possible minimization. So what is the circuit that performs this? And we can try to do some combination to see if the system works. For example, what happens if customer pushes coffee and tea, but no soda? So if we put those variables, we will see that if we put a 1 here, and 0 here, well, since this is inverted, it's going to be 0 here, then it's going to be 0 here, and then it's going to be 0 here. So it's 0 in an AND, it gives us 0 here. If we go to the next, we have 1 here, and 0. So if we put this, then 1 inverted is going to be 0, 0 inverted is going to be 1, 1 here, and the result of this, because it's an AND function, it's 0. We do the same for the final circuit, and the result is also 0. Now, since we have 3 zeros in an OR, then we have 0. So this means that at least in this specific combination, in combination 110, our system or our circuit works. This is the same circuit but using the other symbols. And it does exactly the same, it's just a different way of representing the circuit. Let's see another demo. You're asked to design a logic circuit using basic gates with a VCD input. The logic system should distinguish when the digital is equal or greater than 5. And the input, of course, will be the BCD digit, which can be from anything from 1 to 9. And the output will be 1 if the input is 5, 6, 7, 8, or 9. And of course, it will be 0 if the input is less than 5. So first of all, what is BCD? Well, BCD stands for binary coded decimal. It is, as the name implies, a decimal number which is coded into a binary number. The difference between a VCD and binary is that the VCD codes a single decimal digit exactly into 4 binary digits. Let's see the example for number 15. Well, for number 15, if we want to express number 15 in binary, well, in binary it's, and in binary, this, if we convert this into decimal, this is equal to 15 in base 10. However, a VCD it's not this, because BCD says that we need one digit, one decimal digit, into 4 binary numbers. So if we want to code the number 15 in decimal, we want to code it into VCD, well, we need 1 here, this is 1 digit, the number 1, and we have the number 5, which is another digit. So we have 2 digits, and each digit must go into 4 binary digits. So this will become, well, 4 digits for digit number 1, which would be 0, 0, 0, 1, and 4 digits for binary digits for decimal digit 5. So this would be, so notice how the binary number is very different than the VCD number. So now knowing this, what is the truth table? Well, the truth table is we have 4 digits, which are the 4 digits for the binary code decimal, and we have the output. Now notice here that we have some don't cares. And that is because, well, from this point we have number 10 in decimal. However, 10 in decimal would need 8 binary digits. So this is not a correct input for only one BCD digit. That's why we don't care about numbers in binary that are greater than 10. So the function would be this. It would be the sum of products, of course. Remember that the problem said we want to detect anything that is greater than 5 or equal than 5. So that's why the output is 1 in those scenarios. Now, if we want to implement this, one thing that I forgot to mention here is that we actually don't need the truth table, because if you see, well, here we have the choices or the numbers that we are being asked. In the problem it said we want to detect if it is greater or equal than 5, and you can see that, well, it's a simple matter of putting min term 5 through 9. So we also don't need minimization because we can say, okay, this is the circuit. Well, the circuit, it's all the minterms. This is the minterm number 5, which if it detects a 5 here, if it detects that code, then the output is going to give me 1. So this is minterm 5. And of course, this is minterm 6, this is minterm 7, this is minterm 8, this is minterm 9, and they are all summed in the OR part of the circuit. Now you can ask, what happens with the donkers? Well, since they are donkers, in this circuit we're choosing to put those donkers into 0. However, what happens if we want to minimize? Well, we can put that into a truth table and we can try to find the minimum function. So we have that. We can see that all the groups are essential, and so that would be the function. What would be the circuit? Well, this would be the circuit that detects when the output is greater or equal than 5 in a VCD number. And when we compare two circuits, these two circuits for detecting a VCD number greater than 4, we can see that, of course, we have two very different circuits that both do the same thing. Here's where we can see the advantage of using minimization. So besides regular gates, we also have different possibilities of implementing combinatorial logic functions. For example, we have the option of using only NANDs and NORs, and in this video we will see how to make a circuit with only NANDs. We have the option of using decoders. We have already seen this in other videos. We have the choice of making it with multiplexers, and we also have the option to perform a combinatorial circuit using PLDs. PLDs are programmable logic devices. So what is a NAND? The NAND is a combination of an AND gate followed by a NOT gate. So the function is defined as A.V all inverted. And NAND performs the logical function AND when its input signals are active high, but also with an active low output. The key to understanding the NAND function is to observe that the output is 0 if and only if its inputs are simultaneously 1. And here's the truth table. Again, it's pretty similar to the AND function, where we have both inputs being 1, the output then is going to be 0. So it's pretty similar to the AND function, but inverted. It can also be considered as an active low input or with an active high output. So you can see here that the inputs are active low and the output is active high. Now, some interesting properties of the NAND. Well, what happens if we have the same input into a NAND? If we have the same input, we know by using theorems that A.A is going to give you A, and then the inversion, of course, is going to give you A inverted. Therefore, a NAND gate can be used to generate a NOT gate. We also have another property where if we invert the NOT, then we have a simple, if we invert the NAND, then we have a simple AND. And we also can invert the individual variables. Here I'm going to clarify it a little bit. The normal function of an AND would be A dot B inverted. If we perform the theorem 8, then we know that this would be A inverted or V inverted. So what happens if we invert the variables inside? So if we invert the variable here and the variable here, then we would have another inversion here and another inversion here. So that means that this would become A or B. So we can see that if we invert the inputs of a NAND, then we get an OR. So with these three properties that I just explained, we can use the NAND to construct any of the three basic gates. So how do we construct them? Well, first of all, the AND. The AND, remember, it's by putting the NAND and then a negation. Now here you may think, well, what is this? Well, this is a NAND with both inputs connected to the same input or to the same signal. Here is the OR. The OR, it's inverting the inputs first, then putting them into the NAND. And finally the NOT, where we where we connect both inputs to the same signal. Or we can actually do this also. We can put a NAND, and if we put a NAND here, then in one we put a high, and the other one we put any signal. then here we're going to get that signal inverted. Why is that? Because this is as if you had x dot 1 all inverted, and we know that x dot 1 is x inverted. Now we have another symbol for the OR. So remember the OR, it's this. So instead of putting all the symbols as NANDs, we are changing this symbol. This symbol is this one here. And the reason why is because we can see a little better here that if this is an inversion and this is also an inversion, then both inversions cancel and then we get the OR. So let's see an example. Determine the equation for a system with three inputs, A, B, and C, and the output will be 1 only when exactly one of the inputs is high. And we want to implement a two-level circuit using only NAND gates. So we will build the truth table first. So the function says the output will be 1 only when exactly one of the inputs is high. So here would be 1, then here it will be 1, and also here. All the other inputs are 0. So we already know that this type of problems, it doesn't have a minimization. So we're only going to focus on the first one, on this one here. So what kind of circuits can we make to detect this code? Well, it's a min term. So we need to do something like this. So that part would give me a 1 for that specific combination. So when you are asked to do this, well, what you have to do is make the adjustments to get that same function but using only NANDs. So how can you do it? Well, first I'm going to do a little trick, and I'm going to write the same circuit, but I'm going to do it very big. I'm going to do it again. So now that you know the circuit, I'm going to do the same circuit but using only NANDs. And we're going to use the alternate symbols, or the combination that gives me the same functions but using again only NAND gates. So I'm going to put here the variable A, V, and C. And then the reason why I made this big is because I want to fit the alternate symbols or the NAND symbols inside the normal functions that we are familiar with. So here inside the NOT, I'm going to put the alternate symbol with using NANDs, which is that. Okay, so I'm going to wire this to this NAND. I'm going to do the same here for making this. We have a NAND here with both inputs connected to each other. And for the variable C, of course, I don't do anything. I just put it the same way. Now for the AND, well, for the AND, we perform a NAND, but in order to make the AND, I need to invert this at the end, also using a NAND. So this would be the logic circuit to make this case. Now, here, the interesting part is not this. The interesting part is that if we continue the same circuit by using only NANDs and then putting them in an OR, we would get the following. So that would be the three circuits to detect the three rows. So we need to put them in an OR. If you remember, the OR is a NAND with its inputs inverted. Now, the interesting part here is when we connect this is the correct circuit. Here we have the function. Now we can realize that both this one here and this one here are inversions. So this is as if I had two inversions in a row. So if you remember, if we have A inverted, inverted, then we have A. So that means that I can cross these two because there's no need for me to do 2 times the inversion. And it's the same here. And also it's the same here. So this circuit actually simplifies a lot when we erase those and we realize that we can connect them directly to the NAND. So this is the way you could implement the same function by using only NANDs. Now we also have the same for NORs. Here's the way we can make the same functions with the NORs. And we also have the AND alternate symbol. And that's it.